Hello, everyone. Thank you for coming. It's great that we can meet despite the situation, and we can start by presenting who is going to present today's talk, which is Matt Belcher. How is your surname pronounced, Matt?
That was good. Yes, Matt Belcher.
Belcher, right. Matt is our compañero here, a colleague in Codurance. He's an engineer and a software craft person. He has great experience as a software developer as well as a technical lead. His specialty is to help organizations and improve the capacity of delivery. And he achieved this incorporating good practices and strategic vision in a profound way. So thank you, Matt, for being here.
No problem.
And now we're going to present the whole crew. We are here moving out this, the whole ship. We are Codurance, Codurance in Espanol. For us, it's very important to give back to the community what we receive from it. This is in our DNA. We basically breathe this. In fact, we were a company founded from starting from the software crafters community in London. Our mission is to promote good practices and standards of quality in software industry. And we feel very proud and to contribute to the community that is somehow responsible of our foundation and our development, right? So here I'm going to introduce a little bit how the session is going to work. Now we can turn on the cameras if we want to salute everyone. It's easier for us, especially for Matt, to see friendly faces looking with interesting faces to his work. So if you please can turn on the camera, that would be better. But if not, just feel free to stay like however you feel more comfortable, right? We will have this presentation during the following 45 minutes. And during this time, there's some pauses, small pauses of the content that we will aprovechar, that we will use to ask questions to Matt, either from the chat that you write down or by raising a hand and then asking in the microphone, right? We want to tell you that all the content will be recorded and hang to YouTube. So don't hassle if you don't hassle to write down everything, because there will be a recording of this. And that's pretty much everything. So we can start.
Okay, great. First of all, thanks for coming along today for today's session. I want to talk a little bit about evolutionary architecture today. And here's some of the things that we'll try and cover off today. I'll explain a little bit about what evolutionary architecture is. We'll break down the key components and go through each one. And then we'll talk about how you might start to build your own for your own teams. And then along the way, I'll try and pause for some input and some Q&A. A bit about myself. So I spent about 9 years or so kind of working as a software consultant. Previously, I was at ThoughtWorks for about 8.5 years, sort of leading teams and designing architectures for different systems. I've now joined Codurance, based in London. And throughout my journey, I've worked with lots of different teams, and domains, and various architectures along the way. So before we start, what is architecture? It's a word that we use quite a lot in our industry, but what does it actually mean? And in truth, there there is no real standard term for it in the industry. So instead, let's look at a few quotes from various people that might help us. So first of all, Martin Fowler, he says, software architecture is the decisions which are both important and are hard to change. Simon Brown, he says, architecture is about understanding what you need to build, creating a vision for building it, and making the appropriate design decisions. And finally, Ralph Johnson, he says, architecture is the decisions you wish you could get right early on in the project. So there's something here about things being hard to change and making decisions. And also making the right decisions has a big impact on what we build and how successful that tends to be. But let's think a little bit about the classic process of how we build and design an architecture. And generally it tends to look a bit like this. It's kind of a linear process. So from the beginning we have this kind of architect phase. That's generally where we make most of the hard decisions up front. And then during the develop phase, we sort of pretend to ourselves that that's the easy bit, right? That's kind of writing code, and that tends to be okay, and we're happy with that. And then releasing, well, that's kind of somebody else's job, right? That's a different team or something like that, and that's easy. But in truth, I think we all know that we tend to know the least about the space we're working in, the problem up front. So when we're making all these hard choices during this architect phase, we actually know the least. And we actually learn the most during the development phase. So we uncover false assumptions and we learn more about the domain that we're working in. And actually releasing is difficult, it is hard. And we need to use the right tooling and design for that as a first class thing. So evolutionary architecture proposes the following process instead. So after we release something, we take some time to reflect on that change that we've made. So say we release a new change into production, we then gather some data on that change, and we reflect on whether or not decisions that we made were the right ones. Is our architecture still moving in the right direction? But why is that reflection point so important? Well, I think we all know that the world today is changing at kind of a very fast rate. And if you think about where our software systems run, then one thing really is clear, isn't it? That change is inevitable. Whether we like it or not, our software and our architecture are going to have change thrust upon them. And there's all different types of different change as well. So we could think about change from a tech perspective. So different languages come out, or different libraries and frameworks, even environments. So we have cloud deployments now and serverless, for example. Like they weren't things that were around sort of 5-10 years ago. There's also various sort of non-technical changes as well. So if you think about Netflix and Spotify, for example, people are now renting things rather than buying the physical films or the music now. And that's a different model to what we had before. And those models require us to design systems a bit differently. We also have ever-increasing customer demands as well. So our customers are ever more increasingly demanding richer experiences from our products. And often also supporting different devices, so mobile, tablet, phone, and so forth, as well as new products as well. So we know that change is coming whether we like it or not. It's often very difficult to predict. Evolutionary architecture is all about embracing this fact that change will happen and building upon that concept from the very beginning and trying to build and design for change up front. So my former colleagues wrote a book on this. Neil Ford, Rebecca Parsons and Pat Qua. And their definition of what it means is an evolutionary architecture supports incremental guided change as a first principle along multiple dimensions. So there's quite a lot in that description there, and quite a lot to unpack. So we'll try and sort of go through and actually kind of unpack what that actually means. But before we do that, anything so far people want to comment on, or any questions? No? Okay. In that case, I will carry on. So the first thing is this idea of guided change. What does that actually mean? So it's about setting the direction we want our architecture to go in, and putting in mechanisms to keep it on track, and notify us when we're moving away from that target. The question is, though, how do we know if our architecture is good? How do we know if it's degrading, for example? Well, we can borrow a concept from evolutionary computation to help us here, the idea of fitness functions. So a fitness function represents something you are trying to achieve. So in the evolutionary computation space, you would start off by defining a fitness function, and then the algorithms then attempt to define solutions that match that fitness function's requirements. So we can think about that in the context of architecture, where we're defining what good looks like for our systems. So the naming may be new to you, but I'm quite sure you've used these in the past. So for example, if you had done any form of performance testing, for example, that in itself is a fitness function. You would have set a threshold value for some sort of acceptable performance level, and the test would have either passed or failed, depending on whether it was either above or below that threshold. And that is a fitness function. You have declared an acceptable performance for your system. There's also some nice tools up there that enable fitness functions besides performance. So in the Java world, for example, you have tools like TradeDepend and Arch Unit that enable us to put in automated tests in place around sort of code-based modularity and dependencies within our code. And they're all different types of fitness functions that we can apply to tell us that our systems are growing in the right direction. The key thing, though, about a fitness function is that there should be something that people cannot disagree on. A little bit like defining what done means for a user story. Our target architecture, or what good looks like, if you like, is then the sum of all of our fitness functions together. And the key thing here is that we focus on characteristics and qualities of what we want to build, rather than implementation details. So, for example, we might define up front the level of security and the level of performance we need as part of our target architecture, as opposed to saying, well, I want to use S3 to store data. So we're moving away from implementation details and focusing more on the outcome we want to get, and measuring that along the way. And the key thing here is these fitness functions act as guardrails for your architecture. If you've ever been to a bowling alley, for example, and you see these kind of these barriers down the left and right side of your lane, they're there to prevent the bowling ball going down the side, right, and down the gutter. Fitness functions act as a similar thing for your architecture. They give us feedback when our architecture is moving away from what we've defined as good. So moving and prevent our our architecture falling down that gutter hole, if you like, in the bowling sense. So there are lots of different types of fitness functions. Let's quickly go through them one by one and describe them all. So the first type is atomic fitness functions. So they generally kind of exercise just one aspect of our architecture in isolation. So, for example, a unit test, for example, that checks a code-based modularity. So that's just testing one small part of our architecture atomically. So that would be an atomic fitness function. Whereas on the other scale, you have holistic fitness functions. And these sorts of fitness functions, they they combine multiple fitness functions together. So if you've heard of Chaos Monkey, for example, from Netflix, that is an example of a holistic fitness function that is testing a whole bunch of different qualities together. So you might test, for example, your scalability, your performance, and all these different things as part of the same fitness function. And then we have triggered fitness functions. So these are run based on a certain event occurring, for example. So maybe you trigger a unit test through some script or something like that. That is an example of a triggered fitness function. It requires some manual intervention to trigger the test. And we'll come back to that later on. Continual fitness functions. So these execute a constant verification against our system. So if you've done things, for example, like monitoring-driven development, where you have monitors watching your systems and your live traffic constantly, that is an example of a fitness function that's kind of running continually against your system and giving you feedback on what's going on. We also have static fitness functions. So they have a fixed result. So they either pass or fail. So an example here, for example, could be if you have a unit test that checks the level of complexity in your code base. So beforehand, you and your team, you would have agreed a threshold level of complexity you're happy with for your code base. And you would have written the test to say, if this complexity level goes above that agreed threshold, I want this test to fail. So you can catch early on if the code base does start to increase in complexity. And that would be an example of a static fitness function, because that test has that kind of a static level of threshold that you're able to test against. And then contrary to that, you have dynamic fitness functions. So these rely on a shifting definition based on extra context in the greater world. So for example, if you're degrading performance, that might be okay as a trade-off if you're able to achieve more scalability, for example. Another one might be you're trading off security versus performance. So it's these trade-offs that you'll define as an architect based on your own situation. And then you also have automated fitness functions. So if you use a CI/CD pipeline, for example, these are really good places to run these fitness functions through scripts and those sorts of things and testing frameworks. But we also have some manual fitness functions. So there might be some sort of legal requirement, for example, that's really hard to automate, in which case there may well be a manual step on your part of production where somebody is manually checking our legal compliance and those sorts of things. And that would still be a fitness function, albeit maybe done manually. But it's still a key to capture that process. We also have temporal fitness functions. I've been on a number of projects where I've seen the client get into a situation where they're doing kind of a last-minute panic because they just found out that their certificates for encryption are going to expire soon. So that's quite a common thing that I've seen out in different projects. So that would be a really good example of writing a temporal fitness function. We can write some unit tests that will start to fail as we get nearer and nearer the certificate expiration date to give us an early warning sign that we require to take some action. There's also domain-specific fitness functions. So depending on the domain you're working in, so e-commerce, banking, legal, publishing, whatever it may be, there may be certain fitness functions that you need to pay attention to, certain requirements for legal reasons and things like that. And they're also really important to capture somewhere and ideally automate to be sure that you're building in the right way. So we've looked at the idea of guided change and how the idea of fitness functions can help us. The next thing to look at is this idea of supporting change across multiple dimensions. What does that really mean? So before we dig into that, I'll have a quick pause for people to give questions or any comments so far.
Yeah, if you allow me, Matt. So you're talking about fitness functions as a way to, let's say, evaluate how well that architecture that you're sort of describing or implementing performs, right? And to some extent, it's a bit like, writing the test where you write the code and then making sure that it's used, let's say, as a specification, right? Is that so? Is that what you're referring to then?
Potentially, it kind of depends on the starting point, I suppose. So if you're starting an entirely greenfield project, then absolutely, like that might be where you start from. You have nothing and you define up front, this is what I want my system to look like. And then that will be kind of writing those tests. But also I've seen clients where they already have some systems out there. They're feeling some pain for various reasons. And then we say to them, okay, well, before we kind of go any further, let's take a look at the current state of the world and where do we want to be, and write fitness functions for the things that are important to us. And then that will give us an idea of the current state versus where we want to be. And then we can start monitoring the things and start to improve the things that we really care about.
Right.
Does that make sense?
Yeah, it does. Yeah.
Cool.
In the chat, there are no questions right now.
Okay.
But I will keep looking in case for the next one.
Cool, good stuff. I will carry on in that case. Oops. This idea of having multiple dimensions. What does that really mean? So there's changing requirements from the business as well as the non-functional requirements. So for example, in the UK, there was the whole GDPR requirement that came out a few years ago. And architects have to balance all these different requirements at the same time. And it can be a bit like kind of spinning plates to try and sort of keep all these different requirements in the right direction. A key thing about being an architect is trading off different qualities. So when we think about kind of defining what good looks like for architecture, a big part of that will be addressing the trade-offs that we need to care about. And they are the different dimensions that we'll start to talk about. So the classic one tends to be the trade-off between security and performance, right? So the more things that we encrypt, for example, that's going to have a performance hit. And there may be various there may be various trade-offs that we can make there in terms of amount of encryption versus performance and things like that. So they're the sorts of things that as architects and engineers, that those trade-offs, they are really important. And they'll be different depending on your environment and your context. And that's what we mean by multiple dimensions. It's kind of balancing between the different requirements from the business, but also from sort of performance and scalability and all those sorts of things as well. And then finally, sort of going back to the earlier quote there, the final thing was incremental change. So we mentioned previously that change is inevitable, and whether we like it or not, our architectures will be subject to some sort of change. And when this change does happen, we don't want to have to make large sweeping changes to our architectures to support them. Instead, we want our architecture to allow us to make small incremental changes over time. That allows us to sort of get a nice kind of tight feedback loop in terms of where we're heading as well. So I've mentioned quite a lot the word evolution and kind of evolving so far. If we think a bit about that in terms of biology, for example, evolution happens through generations. So our architectures, in a similar vein, they tend to evolve through releases. So every new release that we do to production in effect is a new generation of our architecture. And then thinking like that, then the thing that we want to optimize for is the ability to evolve fast. So how quickly can we get a new generation of our architecture to production? How quickly can we deploy new versions of our architecture on a regular basis? To do that, we need to adopt a few engineering practices. They act as kind of like foundational layers to be able to build upon later. And we'll sort of have a look through those now and what they mean and what they are. So if we go back to this idea of evolvability and wanting to get to a point where our architectures are able to evolve quickly and can keep pace with the rate of change happening around us, then the key thing to ask ourselves is, what is our current cycle time? And cycle time in the software world with architectures is like kind of that generation between generation time frame. Put more simply, how long does it take us to get a simple change from development all the way into production? That's the sort of the generational time span between one and the other. And the key thing there is that we want to be able to do that in a safe and reliable and a repeatable way, right? And all these things essentially kind of boil down to this idea of continuous delivery, which is majorly important. We need to know that our deployments have been done properly. We need to know what the environment looks like and how it got to that state. And deployments being repeatable and non-events, essentially. I sort of seen some teams sort of celebrate wildly about deploying to production. It's their first time deploying in perhaps sort of 6 months. Celebrations should be about putting features in the hands of your customers rather than deployments to production. Deployments should be dull and boring non-events, really, because you do them so regularly and they're scripted and repeated and automated. The key thing to celebrate more is delivering new features for your customers. And that's kind of really at the core of the idea of sort of CI/CD in effect. And these practices lay the foundation for us to then build and work towards evolving our architectures. So to do this properly, we have to embrace a culture of automation to give us a reliable and repeatable process. So automating how we build our software, how we deploy it, how we build our infrastructure, and so on. And once we have all these things automated, we need somewhere to run them. And that's generally where sort of deployment pipelines, sort of CI/CD pipelines come in. They are really great places for us to execute our fitness functions that we mentioned earlier on. So when we're defining what we want our systems to look like and how we want to evolve our architecture and what that kind of good looks like, having them codified as a set of tests, we can having them run in this deployment pipeline. And having them run there means that they can act as quality gates to ensure that nothing kind of gets to production that would take our architecture in the wrong direction. Anything that would take it in the wrong direction should kind of stop the whole deployment process. So a test should fail when kind of the gate stops and a fix is made, for example. So quite often,
yeah. Excuse me, Matt. We have one question here. Sorry for that, but yeah. Uriol is asking if the fitness functions that can be used as can be tests actually. If these tests of fitness functions can be used as an acceptance criteria for something, and if these acceptance criteria can help to an outside-in approach.
Question. I think the answer to that is yes, absolutely. I think from that kind of outside-in approach, like when we're thinking kind of at the higher level direction of where we want to take our architecture. I think we want to define these things up front. So I think it lends itself well to that kind of way of designing and testing things. Yeah. So in a similar way that we sort of we test drive our features, I think also kind of test driving our architecture in a similar way makes a lot of sense. So yeah, I agree. I think that's an approach that you could definitely follow.
Okay. Thank you. So yeah, we can. I guess we can. If Uriol, if you have more questions on this, Uriol, just keep posting them on the chat, please.
Cool. Okay. Yeah. So sometimes I see teams that do a really good job of having this deployment pipeline with sort of software going through different environments and running tests, and that's all good. But they then kind of have a hard time with the database, and they're not quite sure what to do with the database. So often I've seen teams that have this nice deployment pipeline and there's tests running on against the software, and then if the tests are all green, then that software gets deployed to different test environments. That's all good. And then there's the database, and then there's a whole manual set of processes around how do we update the database and migrate data and all those sorts of things. And I think what I would say and my advice to you would be to include the database in your deployment pipeline. So to have a truly automated and repeatable application deployment, you really need to have all of your changes to the database as part of your release process and that path of production. And to be fair, there are some quite good tools to enable that. So tools like Flyaway, for example, or Liquibase, they enable you to script your database schema changes and have them applied through your deployment pipeline in an incremental way. So you're documenting your changes, but also having them deployed to your database in a reliable and repeatable way, in the same way that we're doing with our software changes. So at this point, I think it's worth to say that components within our architecture, they're going to have to communicate with each other in some way. So Postle's law is an important practice to follow in terms of being able to support evolvability within our architecture. The minute you start to send some data out to the outside world, whether it be via an API response or an event message, other teams will start to expect that piece of data to always be there for them to consume. And whether you know it or not, you have made a contract with that consumer. So Postle's law says, be conservative in what you send, but liberal in what you accept in any communication exchange. So for example, only validate the data that you really need from a message, not the entire message. So if other parts of that message change, it means that you'll have to change your system as well, even though really you shouldn't need to change because you don't rely on that bit of data. So only validate the bit that you really care about. Another key thing with software and architecture is appropriate coupling. Obviously, we need to have some level of coupling between the components in our architectures to allow them to work together well. But too much coupling and things become hard to change. So we want to be able to evolve different parts of our architecture individually based on need. And generally speaking, I tend to think about building systems and components around capabilities. And then capabilities then get combined together to build out user journeys. So for example, you might have a warehousing team and maybe a finance team, maybe a payments team, for example, split around individual capabilities that together can then provide some meaningful end requirements for our customers. So a little bit about coupling at different levels of architecture. So depending on what your current context is and your current level of architecture, there'll be different levels of coupling that you'll have to think about. So for example, if you have a monolith that's unstructured, then you're going to have high coupling between components, whether you like it or not. So changes in one part of the code base, they're going to have an impact on other parts of the code base in ways that you might not predict as well. And that can make things really hard to change and hard to reason about. If you have a modular monolith, for example, then each component communicates via other components via clearly defined interfaces. And then each component is then kind of cohesive functionally. So within one code base, for example, we might have a bunch of different domains and capabilities, but they're all treated as though they were deployed separately, even though in fact they are deployed together, but they communicate via a clearly defined interface, which might be a local method call in the same process, but the code itself is written as though those components could be deployed separately. Microservices. So here you're kind of gaining the fact that you can deploy things independently. So you're kind of breaking apart that deployment coupling. And then the coupling you have there is more about how does your service talk to different services. So what's the API contract, for example? That's that level of coupling you have there. And then in the event-driven world, generally sort of coupling there is quite low, but there is still some coupling, and generally it's around the messages that you consume or you publish and those contracts and those schemas. I think this is a good point to also mention Conway's law. So Melvin Conway, he had quite a famous quote, which was, "Any organization that designs a system will inevitably produce a design whose structure is a copy of the organization's communication structure." That's a really important thing to think about and try to embrace. So what this means is that if we have teams, for example, that are based around functional areas, such as a database team or a UI team or a backend team, then the systems that we build will naturally have these hard separations. And things that are built in this way tend to be quite hard to evolve, which means that we're going to be going down a path where we're building software and architecture that becomes hard to evolve and hard to change. Instead, we want to build teams around capabilities, like I was saying earlier on, that consist of a mix of skill sets and are sort of cross-functional teams. This means that each team has all the skills needed to design, build, and deploy their software. This allows teams, and as a result, our architectures to evolve independently. At that point, I'll stop the questions if anyone has any.
I have some. So then, I guess you're also saying that there is, beyond the actual, let's say, kind of physical structure, no, of the architecture, there's also other layers to that, right? You mentioned the logical layer, right? Like how, let's say, different modules relate to each other inside one unit of deployment, let's say. But also there is an organizational layer, right? Related to how the architecture sort of is able to fulfill those objectives or goals or fitness functions, let's say, that it's trying to, right? Because this is part of the business, right? So is that it?
Yeah, absolutely. Spot on.
It's like different layers of the same thing. Some are more abstract and more relational and related to the organization, but others are more expressed in nice diagrams, no, so to speak.
Yeah, yeah. I think it's really important to bear in mind this kind of Conway law quote, because we might set out with quite noble goals of trying to build architectures in an evolutionary way, but if we have teams that actually are split across completely different boundaries to how we want to design our systems, it's not going to work out well for us. Like if we want to have systems that can evolve independently and be deployed independently, but actually we have a UI team as well in the front end, and we have a database team doing the back end, you have coupling there whether you like it or not, and that's going to impact your chance to kind of get to where you want to be with your architecture. So what I'm saying with this slide is that actually think about inversing the Conway's law. So think about what systems you want to build, what level of coupling do you want, and then design your teams around that. So you may, for example, decide, actually, I really want a payments team who are going to be our experts in payments, and they're going to know everything about payments, and they're going to be enabled to handle all of the payment journeys. So to do that, they're going to need a bunch of different skill sets for sure. So bring all these people together in one team, so you have a cross-functional skill set team, and they are now your payments team, and they can evolve and build their systems independently. So you have that low coupling then between different teams and systems.
Yeah, and it happens with all those, right? Like even if you have, for instance, if the same mismatch could happen between, before you were talking about deployment and the logical structure, right? So if you have monolith and then you're trying to move to something like microservices, but you don't manage to properly decouple those things, you end up with a distributed monolith, right? And then your pain is even greater, because now you multiply your pain, right?
Yeah, very much. That's a really good point. I've seen that happen, I think, many times so far. People they want to jump towards microservices, if you like, without actually knowing where their domain boundaries should be. So my advice tends to be that if you want to get to microservices and you think that's a good fit for you, start off with a modular monolith, where you have all of your bounded context kind of arranged in one code base. Because if you get to a point where you realize actually like what I thought was correct bounded context and correct domain boundaries actually might not be correct, like fixing that in one code base is quite easy. Fixing it across different code bases with different communications through APIs, that's a lot harder. So once you have a better sense of your domain boundaries, and by that point you've also kind of got to a point where you understand your architecture and you've got a good set of tests that are automated and a good pipeline, then think about maybe having moving more towards microservices at that point.
Just one more question, Matt.
Yeah, sure.
What about if you have multiple products that have different requirements, and this makes you to decide different architectures? Since we are coupling the organization to the architecture, it's not that difficult, because then you will have two organizations.
I think if it's sort of one organization that's building multiple products, if you're a product company, for example, I would treat them as two separate architectures, and they may well have very different requirements as well. So you probably have a different sort of fitness functions for each one. One, like for example, one might require some really strict rules around performance, and you might have kind of really high latency, whereas one actually might not care so much about that performance. So I'll generally treat them as two separate things.
Okay, thank you.
Cool. Okay, I will get on. So, so given what we said so far, where would you start with an evolutionary architecture? How would you begin? And generally speaking, there's kind of 4 or 5 different steps that I would sort of recommend people start to do. So first of all is identify dimension effect by evolution. So in effect, like what are the things that you care about most in the architecture, and what are the things that you are most worried about, and capture those things and try and define fitness functions for those things. So it might be that you're really worried about performance in your system, for example, but you're not really sure what the current level is. You've heard people say, oh, this is really slow and customers unhappy, and so forth. So what I would say was define what you want, where you want to be with performance, capture that as a fitness function, ideally in a performance test that you can kind of run in the pipeline, and capture some metrics kind of where you are currently based on that metric. And chances are maybe you're not quite at that level yet and you have some work to do, but that's fine. At least now you know kind of where you are in regards to that threshold value. And then kind of like, as you do some work to progress with your performance, that test should hopefully then start to turn green once you get to the point where you're below that threshold. So use deployment pipelines to automate your fitness functions. They're a really good place to execute these fitness functions. So a good deployment pipeline should map out the path that our software needs to take to get to production. And so by placing these fitness functions in our pipeline, they act as kind of guardrails to make sure that we're not doing anything that kind of veers us off course. But the key thing is that all these things require the foundational practices of CI/CD. So without those in place properly, all these things are going to be difficult for you. So in the same way that I see teams will jump towards microservices, you need to have the foundation of CI/CD first to do that. It's the same with here as well. So you need to be having a good grasp on CI/CD practices. So then think about evolutionary architectures, because they kind of build upon each other. So we talk about deployment pipelines, for example. That is a CI/CD kind of practice that is fundamental, really, embracing automation and all those sorts of things. And then, so continually evaluate the fitness functions. So don't just write them and leave them. Make sure that they are constantly under evaluation, and make sure that you have a good grasp of, are the thresholds still correct? Should I change them? Is it still matching kind of where I want to go? And I've seen teams that have kind of once a fortnight like get together and review these fitness function tests and say, okay, well, actually, this one's probably not quite where it should be. Let's change the threshold. Or actually, given some new requirements have come in, let's think about different trade-offs here. Maybe we want to trade more in this way, and tweak our tests to be more close to where we want to head. And finally, kind of be pragmatic and take it slow. You might start off with writing some unit tests, for example, around performance. And perhaps as a first step, those tests don't fail the build. Maybe they just kind of print a warning, for example. So you can see where you currently are. And once you get to a point where those tests are passing, that's the point where you can kind of enable them to fail the build. So it's that kind of small step where you're capturing the fitness function, you're having it running in your pipeline, you do some work to make it pass, and then you have that test in the pipeline that can fail the build, so you protect it against kind of degrading down further. So with all that though, which systems should kind of be focusing on first? If we're thinking about evolutionary architectures in our organizations, where should we be best focus our efforts? So quite often there's a whole bunch of different systems. Where should we be best focus our efforts? And generally speaking, I think it's useful to think about systems in kind of 4 different categories. So you generally have these systems that are commodity based. So these systems on the bottom left corner here, these don't really require much change at all, and they don't really generate much value. So an email server, for example. Doesn't really change that much, but it doesn't add a lot of value. And then we have support systems. So support systems, they generally help us to do our work in building software. So for example, tools like Jira, for example, they help us in writing user stories, but they're more supporting tools than anything else. So here we might want some level of customization, but it's not a really key system for our company. And then in the top, we have these kind of experimental systems. So perhaps we're making a bet based on an idea about the market we're working in. In this case, we're looking to just test out an idea with these sort of systems. And so whilst their value could be quite high, we don't really require much change for them. It's more a case of we'll build something, put it in the market, test the idea out. If that idea seems successful, we'll then kind of move into a different phase where we build the system for more future-proof. And then finally, on the top right here, we have these strategic systems. And those systems, they're the ones that add real value to our business. And they need support. And they need the requirement to be able to support business change constantly. This is where I would recommend that you focus your efforts in trying to apply evolutionary architecture. The other three quadrants they're not really a good fit for that. These types of systems are the ones that you'll get the biggest benefit, because these systems, they need to be able to support the changing needs of our business. And so by using that as a yardstick, it's generally a good fit for evolutionary architecture. And finally, some pitfalls to kind of keep an eye out for with evolutionary architectures. So there's the last 10% trap. Avoid adopting tools that are on the face of it providing almost what you need. Whilst you might get a short-term gain on productivity, eventually there'll be a business need that doesn't quite fit the tool that you have. And you'll find yourself spending a large amount of time delivering that final 10%. For example, there could be a wrong model or wrong abstraction for your particular problem that you need to solve. The other is coding via config. Configuration does get quite complicated quite quickly. You might be using a UI, for example, to set different config values for a tool. Over time, though, you'll want faster and faster feedback from that config change, which means that you'll start thinking about treating your config as code and having tests around it and having it kind of running through a deployment pipeline and releasing it to different environments and all those sorts of things. The next one is product customization. So buying products off the shelf is totally fine if that makes sense for your space and your domain. The key thing to think about, though, is how much customization that is going to be done to match your needs by the vendor. It means you're very tied to the product vendor and their roadmap. So, for example, you might need a particular important change to be made to that product by the vendor to support a new important feature for your business. But you'll be competing with the rest of the other items on that vendor's backlog. And so your priority might not match their priority, and it might restrict your time to market. And finally, exuberant coupling. So have a think about the different types of coupling in your architecture and what levels of cohesion you really need. There may be couplings that are creeping in there that don't really need to be there, and just have a think about the right level of coupling for your architecture. So that's kind of all I have for today. If you're keen to learn more, there's really good books and really good resources. The website there has quite a nice page on different fitness functions. So you can kind of go in and there's different sort of examples for you, and you then have to kind of go away and write the fitness function to match that question. So that's quite a good way of testing how you would go about writing fitness functions for different situations. That's all I had. Thanks.
Thank you, Matt.
Thank you, Matt.
Thanks.
Thanks a lot.
So maybe we can pass to some questions if there are some questions left.
Yeah, sure.
Yeah. Please feel free to ask.
Or to make comments, or
Yeah, to make comments. Yeah, whatever feedback is good. I will give my comments here. I liked a lot how the fitness functions would cover many different aspects. No, you said you call it dimensions. No, so for me, fitness functions was something related to performance at a infrastructure level, something like this. But I mean, when you say that fitness function is everything you want to improve or you want to keep an eye on it, yeah, then the definition changes to something more wide and find it.
Yeah, so for example, I can remember, I think it was last year, working with a team where we were trying to increase the level of modularity in our code base. So it was a monolith code base. It was a single deployment, and we were working towards eventually sort of breaking it out into microservices. But we knew that before we did that, we had to have a better way of designing the monolith internally first to know where the different bounded contexts and domains would be. So we had some meetings and we decided kind of what we thought the correct boundaries should be. We kind of rearranged the code base so it kind of matched these boundaries. But then we wrote some tests, which made sure that we didn't introduce coupling between these bounded contexts in the code base, which meant that these acted as fitness functions for the code base, right? So if any change were to go into the code base, that would mean that we would break that modularity. Those tests would fail, and they would tell us that actually the code base is moving in the wrong direction against what we had agreed.
Thank you. Yeah, it's very, very interesting. Thank you.
The thing is, in the sense, Visual Studio has something like that, right? The enterprise version a couple of years back introduced the whole, check the architecture kind of thing, right? Where you could like have a diagram and actually it will sort of like force you. I don't remember if at compile time or what, but it will tell you, right? Like, hey, you're talking to, I don't know, the database directly, right? Or you're skipping on some of this stuff, right?
Yeah.
So. Like that. Yeah.
And one other question, Matt. You talk about small increments on every release of the architecture. Can you give some examples that has worked for you, or provide some more explanation? Yeah.
I guess generally speaking, it's kind of going back to the idea of optimizing for new generations of the architecture, right? So the smallest possible thing that you can deploy to production that adds value, that should be the unit that you increment, that you kind of like deploy to. So it might be, for example, that you start off with an API endpoint that maybe just returns canned data, for example, and then you deploy that to production, and then you start iterating on that deployment, on that API, sorry.
Okay.
So, for example, I can remember deploying a really basic Hello World application for a code base. It didn't do very much. It had a single API that would just say Hello World. But it was important because it enabled us to build out that path to production and understand how we got to production, understand how we would deploy the software, understand how we would write the first couple of unit tests. And so there was a whole lot of value in kind of in learning and setting up that deployment pipeline. Whilst the software increment itself was quite small. So we got a big payoff in terms of learning and feedback, but the increment itself was quite small.
Oh, thank you. Thank you.
There's another aspect to this because somehow we talk, we touch on a lot of subjects, right? But the idea of having this sort of like feedback loop, right, where you define those fitness functions, or a way to evaluate the architecture, then you get it out as fast as possible, or you deploy it, then you evaluate, etc. Right? But then I guess there's a part to be explored there. Maybe you could shed a bit more light on that, on the how do you come up with the actual architecture, right? Because when you're doing the idea of if you do the comparison with TDD, right, and emergent design when you're writing tests, that kind of stuff, could you talk a little bit about that? Like, how do you actually evaluate your proposed solution on how to solve or how to come up with those decisions, right? Because one thing is copying, oh yeah, we need to create microservices, right? But that's sadly that's not the solution always. So yeah, if you want to explore a bit more on that.
Yeah, good question. So generally, I think thinking about these, I think it's quite context dependent. So for example, what I might say is, can you tie back your architecture to company goals and what's important for the company? So for example, to put it in a bit more context and a bit more detail, you might say that actually a really important thing for us is time to market and speed to market, and we don't want to be owning any kind of infrastructure. We want to outsource all of that. We really want to focus on building the core software that we can add value to. And so, okay, well, that's interesting. So then you start thinking about, okay, well, given all those things that are important to the company, they then feed into characteristics that we want from our architecture, and they in themselves become fitness functions. So to put that in a bit more concrete terms, if you care about things like speed to market, then you want something that you're going to be able to kind of get really quick feedback on and quick tooling around. So for example, you might look at Amazon, for example, AWS, because that gives you that quick speed to market of being able to kind of plug and play different tools and spin up things rather than having to manually do it yourself. You might look at so that way you're not building your own infrastructure, you're reusing services from other companies. That's just one example. But so generally speaking, I tried to think of it in that way. So generally the company has some goals and direction of where they want to be. And then how do you map that to your architecture? And they act as kind of inputs into fitness functions and qualities that you should be able to exhibit in your architecture. So
the idea of, you start with the business, right? Because in the end, technology is just a means to, start with the goal, and then from there, see what are the, it could be something like, we need to scale up and down really fast, or we need, as you mentioned before, right? We want to get it out there as soon as possible, so we don't really want to be boggled with having to manage this stuff, right? Like if we can streamline that, that's perfect, right? And then from there, go into more of a, what are the scenarios then? How does this look, with this architectural goals, right? What are the key scenarios that we need to plan for, right? And from there, I guess you start creating your fitness function, right? Like, or fitness functions, right? Like the idea of, a customer journey could be a fitness function, right? Like that, it's a scenario that you need to be able to fit in, right?
Yeah. So for example, if you're in an e-commerce website, for example, or you're an e-commerce company, you might sort of take company goals and then say, okay, well, what are the different capabilities that we need to stitch together? So you might say, okay, well, we need some way of taking payments. We need some way of, I don't know, warehousing stock. So these capabilities that you identify, they then become the teams that you need to build. And then for each team, you can then drill down again and say, okay, well, what are the qualities that this capability needs to exhibit? And then that then drives the design and how you want to build out that particular system.
And there's also the aspect of, you have cross cutting concerns around the architecture also, right? Stuff that it might not be directly related to the goals that you're trying to achieve, but would definitely be, security, observability, all these things, right? And those are definitely something to
Yeah, very much so, yeah.
Just one thing. We're noticing here that there's many people joining us since 7 p.m. in Barcelona time. We think that there might have been a confusion with the starting time, and the meetup is finishing right now. So to all the people that has just joined, we feel extremely sorry for that. And in case you want to hear what Matt just explained, we provide a YouTube video at the list where we're putting in the chat. So we're sincerely want to apologize for that.
Let's meet in the middle, 5.2.
Yeah, just a second. So sorry for that, and hope we can see in the next one, or we can even ask Matt to do it one other day. Just in case.
If people are keen to hear more, I'm happy to do it again.
Yeah. So
don't worry. Do you have the video on demand at our YouTube channel? Don't worry.
Sorry for that. And
but at the meetup is clear the hour. I think so.
Okay. So what we can do is like like if you have more questions on the things that Matt explained during the past minutes, go ahead, and if not, please refer to the video. And sorry for that. Yeah. Okay. So
thank you to
Thanks,
everyone.
Thank you very much. Thank you very much, Matt.
Thank you, Matt.
It's great to have workshops across London and Barcelona. Thank you very much, everyone. Bye bye.
Bye, everyone.
Thank you. Bye. See you soon.